My name is Drew Harper, and I'm an engineer with the California Lighting Technology Center, and I was the project manager for this project I want to talk about. Purpose of this presentation in this project was to evaluate the performance of distributed DC lighting systems. So as many of you know, most commercial buildings use AC or alternating current power distribution systems that receive electricity directly from the grid. Because of this, most subsystems in these buildings, including lighting, are designed to be powered directly off this AC infrastructure. However, most common LED lighting systems and most other digital electronics require DC power to operate. This necessitates an AC to DC conversion for every instance where DC power is needed. And in theory, with increasing DC load, the AC to DC conversion efficiency will improve, and therefore it could be more efficient to aggregate the AC to DC conversion and distribute DC power throughout a building. So again, the theory is that with increasing scale of AC to DC conversion, this could result in a higher AC to DC conversion efficiency. With this in mind, there are two general approaches to a distributed DC power system. The first would be to aggregate and centralize the AC to DC conversion, and this can happen at a variety of scales. A power supply could distribute DC power throughout a whole building. You could have centralized power supplies to power individual rooms of a building, or you could have centralized power supplies for each building subsystem. And the second method is to get the DC power directly from renewables like solar and wind. Although in practice, most of these renewable systems invert the power and feed it back to the grid, or they use an energy storage system rather than directly powering DC devices. So there are some advantages, potential advantages and disadvantages to a DC lighting system. Some of the advantages are, again, there's that higher theoretical AC to DC conversion efficiency. You can utilize existing building infrastructure. We'll talk about it in a minute, but the PoE system or power over Ethernet system can piggyback off of existing IT or information technology infrastructure. They can be safer and cheaper to install since they're classified as low voltage class 2 electrical systems per NEC. However, there are also some drawbacks to DC lighting systems. There can be an increase in electrical losses in the conductor since you're transmitting DC power instead of AC power. There's currently a higher upfront cost associated with these DC lighting systems compared to comparable AC systems. And there's also a lack of standardization between manufacturers in terms of cabling, connectors, and communication protocols. And also many of these DC lighting systems are pretty new, so they could be unfamiliar to the people who are actually installing them. All right, so we conducted a market assessment and identified 12 manufacturers that had commercially available DC offerings. These DC lighting systems, we then subdivided into two main categories: power over Ethernet or PoE, and low voltage DC, which we have referred to as LVDC. And we'll get into both of those in the next slide. We also spoke to lighting reps and electrical distributors to identify a widely used AC lighting system that could be our control or a baseline. So yes, some of the differences between these two categorizations that we came up with. As I mentioned earlier, PoE lighting systems can use, or they do use, information technology infrastructure such as power switches, CAT cables, routers, and IP communication. They also conform to Cisco's UPoE standard, and they operate below 60 volts DC and 60 watts DC per channel. They're capable of transmitting both power and data across the same CAT cable. And again, they're class 2 electrical systems per NEC. The LVDC systems are, they also operate below 60 volts DC, but there's no standardized cabling or communication protocol across manufacturers. And because of this, there's a wide range of possible power outputs per channel, and data and power can be transmitted on the same cable or separate cable. So PoE is a more specific version of LVDC, if you will. All right. So to specify our AC baseline system, again, we spoke with multiple electrical distributors and identified this 2x4 LED luminaire as a commonly used commercial AC luminaire. For the study, we procured 9 2x4 luminaires with a 4,000 lumen output at 35.5 watts or 116 lumens per watt, a correlated color temperature of 3,500 Kelvin with a 0 to 10 volt dimmable driver. the low voltage DC system, we purchased this 9-channel LED driver. It has 9 output channels with a maximum of 226 watts of DC power. It communicates via DMX protocol. And as a load to this power supply, we procured 9 2x2 LED luminaires with 2018 lumen output at 16 watts or 126 lumen per watts. They're capable of dimming down to 0.2% and have a maximum cable run between the power supply and the luminaire of 150 feet. 2 things to note at this point. When we specified each DC system, we wanted to maximize the load that we could put on the power supply. So we picked luminaires with the highest rated wattage that we could find. And secondly, in terms of system architecture, this LVDC system is the most basic of the DC systems that we looked at, and in that it's essentially one centralized driver for 9 luminaires, and that's pretty much it. Speaking of system architecture, before we get into the specifics of the PoE systems that we evaluated, it'd be good to talk about what a PoE system architecture looks like. So basically, a PoE architecture consists of 4 main components. First, you have a gateway computer that hosts the control software. It allows for programming and commissioning of the system, as well as it provides a user interface for the system. Then you have your PoE switch, which acts as a power supply for the system, but also handles communication between the node and the gateway. And then finally, you have your PoE node, which is basically a communication endpoint, and it provides DC to DC conversion and current regulation to the luminaire. And then finally, you have your luminaire, which is similar to a traditional luminaire, but it's driven by this PoE node instead of an LED driver. So the first of the 2 PoE systems we looked at, which we'll refer to as DC Manufacturer 2, we procured this 8-port power switch that has 480 watts of output power. It is also conforms to the Cisco UPoE standard, as all PoE systems do. And then as a load for the power switch, we procured 8 2x4 PoE-enabled luminaires that have 6,500 lumen output at 50 watts or 131 lumen per watt. And again, in order to load the power switch as much as possible, we bought the biggest luminaire, 50-watt luminaire that they offered. And then finally, there's the PoE node, which is attached to each luminaire. Again, it handles the communication from the power switch, and then it gives regulated current and voltage to the luminaire as needed. Oh, skip one. All right. Second PoE system we looked at, which we'll refer to as DC Manufacturer 3. Similar to the first, we use the exact same power switch. In fact, most PoE systems that we could find, the manufacturer suggested to use this power switch. So we use the same power switch, and then as a load on the power switch, we went with this. We bought 8 of these 40-watt white tunable LED luminaires. So these luminaires are, again, they're 40 watts. They're actually white tunable, and they have integrated sensors. And for this study, we weren't interested in color tuning or in the sensors. We just wanted the luminaire we could buy for the system that had the highest wattage. So this was the one. And then here it's important to point out 2 main differences between the 2 PoE systems that we looked at that actually did impact the findings. So one main difference is that the DC Manufacturer 2 system allows you to dim the luminaires through the user interface. So basically, you could sit at a screen and you could dim all the luminaires to whatever setting you wanted to. The DC Manufacturer 3 system does not allow you to do any dimming unless it sees a PoE-compatible dimmer switch on the network. So basically, the other system, you could have only luminaires connected and you can still dim it through a software interface. But for this system, if you don't have a dimmer switch connected, it will not allow you to dim. And we'll get into why that's important later. Another thing to note is that the DC Manufacturer 2 system, let's see if I can go back a slide. As you can see here, the PoE node has 2 RJ45 connectors. One is for power in, and then the other is to allow you to connect another PoE-enabled device in series. What that allows you to do is you can hook up all 8 luminaires to each of the 8 ports of the PoE switch, but if you wanted to hook up a sensor or a wall switch, you could daisy chain it off of one of these fixtures and not have it occupy one of the 8 ports. So where that factors in is that in our evaluation, we varied the load on the power switch in two different ways. And basically, when it came time to vary the load via dimming all the lights at once for the DC manufacturer 3 system, we had to plug in the dimmer switch directly into one of the 8 ports of the power switch, thereby not allowing us to fully load the power switch with 8 luminaires. We could only use 7 because it had to have a dimmer switch, and you're not allowed to daisy chain things or sensors or wall switches with the DC manufacturer 3 system. So hopefully in a bit, it'll become a little more clear how that impacted the findings. So for our laboratory evaluation, we use a California Instruments function generator as a highly stable AC power supply to provide power for the entire lighting system rather than plugging it into mains voltage. And to take electrical measurements, we use both a Zytron 2802 power analyzer and a Yokogawa power analyzer to measure current and voltage at various points throughout the system. So our lab setup consisted of these testing racks you can see on the right that house the 8 or 9 luminaires with enough space in between them to allow them to thermally stabilize. When taking measurements, we placed 1 luminaire on the benchtop and connected our meters as seen on the right, while the remaining 7 or 8 were on the rack. And then for each system, again, everything was powered by that California Instruments function generator, and we collected all of our data using those 2 power analyzers. So in order to characterize the performance of each system, we first identified every point of power loss within the system. Essentially, we took electrical measurements before and after every point where power is either consumed, transformed, rectified, etc. On the right, you can see a generalized diagram to exemplify this. And after we identified every point of power loss, we then varied the load on the power supply in 2 different ways to evaluate its performance under different operating conditions. So the 2 methods of varying load on the power supply were first, dimming all luminaires in set increments and taking measurements at each step. So for example, we set all 8 luminaires to 100% output, take measurements. Then we dim all luminaires to 90% and take measurements, and so on. And secondly, there's a method of sequentially removing 1 luminaire from the power supply while the remaining luminaires operate at 100% output. So for example, set all 8 luminaires to 100%, take measurement, unplug 1 luminaire from the power switch, set all 7 to 100%, take measurements, remove another one, and repeat. Both methods of varying load were intended to replicate the real world, help us understand what the optimal conditions were for this lighting, for each lighting system. So for example, is it more efficient to run all luminaires at 80% or to remove one of them or to turn 1 or 2 of them off? So we made 2 primary assumptions during our testing. First was that the luminaires that were sitting on the rack were performing exactly the same as the luminaire that was being probed. This assumption allowed us to only meter 1 luminaire at a time. The second was that the lighting systems were operating under what we considered to be the worst case scenario in terms of cabling. So for each lighting system, we used the maximum cable length and the smallest cable gauge recommended by the manufacturer. So for the PoE systems, this looked like 100 meters of 24 gauge Cat 5e cable. And for the LVDC system, this was 46 meters of 18 gauge stranded cable. And then before taking any measurements, we allowed all the luminaires to thermally stabilize per LM79. And finally, we devised the following performance metrics to evaluate each system. You have power supply efficiency, which was defined as the total DC power out of the power supply divided by the AC input power to the power supply. Then there's line loss, which was defined as the difference between the DC power at the node and the DC power at the output of the power supply. And there's the node efficiency, which is defined as the DC power out of the node divided by the DC power into the node. And then there's peripheral power consumption, which is defined as the AC power into all peripheral devices such as gateways, routers, etc. And then there's total system efficiency, which is defined as the DC power at the luminaire divided by the total AC input power plus any peripheral power consumption. So for the baseline AC system, we only conducted the dimming test as there's no centralized power supply to remove luminaires from. So the sequential test didn't really make sense. The only source of power loss in the AC system was from the AC to DC conversion at the driver, and this system was able to achieve a maximum efficiency of 86%. Okay, the LVDC system achieved a maximum system efficiency of 79%. The graph on the right shows the system efficiency for each testing method. So as you can see, there's minimal difference in performance between the two for this system. Additionally, the line losses for this system and for all the DC systems matched the predicted line losses that we calculated using physics and the known resistance of the conductors. For the PoE systems, the power switches performed better when varying the load by removing fixtures rather than dimming. So on the graph on the right, you can see both DC manufacturer 2 and 3 performed slightly better when the power switch was when the power switch load was varied by removing luminaires as opposed to dimming all the luminaires. So the node efficiency for each system were determined during the dimming test to characterize the node performance across the full range of luminaire output. The DC manufacturer 2 system achieved a maximum node efficiency of 92% compared to 89% max node efficiency of the DC manufacturer 3 system. It should be noted that the DC manufacturer 3 system was unable to load the power switch as much as the DC manufacturer 2 system due to requiring the use of a dimmer switch in place of one of the 8 luminaires. So if you think about it, when I mentioned earlier, the theory is that if you load your AC to DC conversion as much as possible, so if your power switch is 480 watts, in theory, the conversion efficiency will be optimal the higher the load you put on it. So the DC manufacturer 2 system was able to load the power switch more than the DC manufacturer 3 system. So that could have contributed to why it achieved a higher efficiency. Then we have total system efficiency. So the DC manufacturer 2 system was able to achieve a maximum efficiency of 75% total system efficiency compared to 73% for the DC manufacturer 3 system. And this could partially be contributed to the greater node losses in the DC manufacturer 3 system. All right. Okay, overall, the baseline AC system achieved the highest maximum system efficiency of 86% under our testing conditions, and this was 7 to 13% better than each of the DC systems. For each system, the greatest source of power loss was that AC to DC conversion. Losses due to DC to DC conversion at the node also contributed significantly to the overall power losses, even with a node efficiency of upwards of 92%. Additionally, line losses were as significant, if not more significant, than node losses. And the peripheral losses, however, were less than 2% and would be even smaller for a larger capacity system, as you wouldn't need to have another gateway or another computer to run a 2000 watt system, for example. As I mentioned earlier, we tested these systems under what we considered to be the worst case scenario in terms of cable length. Realizing that it's unrealistic to have 8 luminaires that are 100 meters away from the power supply, we generated computer models to determine what real-world cable lengths might actually look like. To do this, we set the following constraints in the model. The number of luminaires is either 8 or 9, depending on the system. There was a target light level of 27 foot candles at 2.5 feet above the floor, a power density of between 0.23 and 0.3 watts per square foot, and 10-foot ceilings. We also assumed the power supply was located in the plenum directly above the center of the room. And then we let the software generate optimal lighting layouts from which we could calculate the distance from each luminaire to the center of the room and therefore get cable length.
Andrew, we have just like a 1 minute left.
Okay, I have just one more slide, I'm almost done.
Sounds great.
This table shows the results of the computer modeling, and as you can see, the real-world cable lengths were significantly shorter than the worst-case scenario. Using these new cable lengths, we could calculate new line losses and the new system efficiencies for each system. And as you would expect, each system did perform better with the more realistic cable lengths as the line losses were less. However, each DC system was 5 to 9% less efficient than the AC system, even with this factored in. So in conclusion, the AC baseline system is more efficient than the DC systems across their operating range. The DC systems introduce additional sources of power loss compared to the AC systems in peripheral losses, line losses, and losses for DC to DC conversion. The PoE system had more points of power loss than the LVDC system. And also our testing seemed to confirm or seem to agree with the fact that with higher loading on the power supply, you get a higher AC to DC conversion efficiency. And finally, the real world cable lengths would be significantly shorter than the worst case scenario. And finally, the next steps, the study only analyzed DC systems of upwards of 480 watts when there are systems that go up to 2000 watts. So an evaluation of these higher capacity systems could show that the increased AC to DC conversion efficiency is enough to offset the other sources of power loss, making it as, if not more efficient than a baseline AC system. However, there are also AC systems that advertise efficiencies upwards of 90 or over 90%. So those should also be considered too. And finally, an internet-enabled AC system, for example, would suffer efficiency penalties from peripheral devices such as a router, but it would make it more comparable in terms of control to the DC systems we evaluated. So we should look at AC systems that have better controls capabilities as well.
My name is Greg Miller, and I'm a PhD student in the Energy Graduate Group here at UC Davis, and my research focuses mostly on carbon-aware energy loads in the commercial and industrial sector. And the research that I'm going to be presenting on today kind of gets at the question more broadly of how we measure carbon emissions in California and what impact that can have on how quickly and effectively we decarbonize our electric grid. So in the past, there's been a lot of focus on energy efficiency measured with the metric of kilowatt hours. And now more and more, we're seeing that GHG is kind of becoming the currency of how we measure the effectiveness of programs as more focus becomes placed on decarbonizing our economy. So one example is that a current project I'm working on with the Center for Water Energy Efficiency is evaluating the potential to shift the timing of water pumping at water utilities to align load better with low carbon times of day. So using more energy when renewables are available and demand less from the dirtiest plants. And we basically need to be able to know when these cleanest and dirtiest times are in order to shift this load effectively. And this is kind of an example of a broader need, which is to decarbonize the electric grid as quickly as possible. We need to be able to accurately measure carbon emissions in order to make effective decisions about the fastest path to decarbonizations. And so currently there's kind of two main ways that we measure carbon emissions. The first method is with average emissions, which measure for some period of time how much GHG was emitted by all power plants per unit of electricity consumed. And these average factors are typically used for historical emissions accounting purposes in greenhouse gas inventories set by standards such as the Climate Registry and the GHG Protocol. And these average factors are fairly accurate as most of the power plant emissions are measured and reported, but while they give us an accurate picture of historical emissions attribution, they're not really useful for consequential analysis or forward decision making. So questions such as, will installing solar or wind displace more emissions in my region? Will electrifying our housing stock increase or decrease emissions? Or when should I charge and discharge my battery to use the most renewable energy and displace the greatest amount of fossil fuels? And this is because when you plug in some sort of load, like an electric vehicle, for example, it's not all power plants that ramp up equally to meet that demand, but rather there's a small number of what we call marginal plants that respond. So let's look at a kind of an illustration here. Is that on the left we have energy loads, on the right we have generators, and the amount of generation illustrated by the green and blue bars matches the amount of load currently. And generally power plants are turned on in order from lowest cost to highest cost. So we can see here that the two cheapest sources are generating and the expensive coal plant at the top is not. However, if we plug in an electric vehicle, for example, the wind and solar are already generating at their max. So we have to turn on the next most expensive resource, which is that coal plant, to respond to that load. Likewise, if we were to stop charging, it's the coal plant that's going to reduce its generation while the wind and solar remain the same. So in this case, we'd call the coal plant the marginal generator, and it's the emissions from this specific plant that we care about rather than the average from the entire grid. Thus, for this type of decision making, we want to use marginal rather than average emissions factors. But the issue with these marginal factors is that unlike with average emissions, we've been unable to kind of directly measure or identify which plants are marginal and thus what their emissions are. This is mostly because the market operators like the independent system operators like CAISO in California have historically considered information about which units are setting the market clearing prices as market sensitive data that could potentially be used to somehow manipulate or distort the markets if made publicly available. And so it means that these marginal emissions have had to be modeled and estimated. And over the past 2 decades, there's been 4 main modeling approaches that have kind of evolved to estimate these marginal emissions. The first is an engineering model, which basically uses some power flow simulation to simulate the electric grid and what plant would actually be responding to increases in load. A second is a load curve model. So kind of like this illustration here, you build a supply curve by ordering your generators from least cost to highest cost, and you basically then find out where your energy demand intersects that supply curve to figure out which generator is marginal. The third approach is kind of a regression model, which is using historical emissions and load data. You regress the change in emissions on the change in demand to see how emissions respond to load. And in the academic literature, at least, it seems like this is kind of like the most used model now and kind of most trusted. And there's a fourth method based on LMP or locational marginal prices, which are basically the wholesale market prices for electricity, which represent the marginal cost of generation. And the theory behind this is that these LMPs represent marginal costs, which then you could use some calculations to translate into marginal rate of emissions. And it's this final LMP approach that's basically used in California for most policy making around marginal emissions. And there's variants of this one single method that are used for a wide range of policy processes, including cost effectiveness evaluations, building energy code design, time-dependent valuation, rate design, cost shift analysis, integrated resource planning, and energy efficiency reporting. But a couple of years ago, one program in particular, which is the SGIP program, which incentivizes behind-the-meter energy storage, gained a lot of media attention, at least in the energy world, because it was found that these batteries were actually increasing greenhouse gas emissions because they were simply optimizing based on the cost of energy. And so this was a big problem, and a working group was convened, and they ended up using the same methodology that had been used in these other applications to an adapted way to provide an emission signal to incentivize batteries to reduce their greenhouse gas emissions. So how does this method work? Well, basically what it's trying to do is calculate a heat rate of the marginal plant, which describes how much fuel that plant is consuming per amount of electricity it generates, based on the locational marginal price, and then getting the marginal emissions rate from that. And the primary assumption of this method is that natural gas is the marginal fuel in all hours. So to get that heat rate, basically what it does is it subtracts the average variable operating and maintenance costs from the LMP price, which in theory should leave you with just the cost of the fuel consumed by that plant. And then once you have that fuel cost, you can divide by the total price of gas, which includes the fuel price and also the GHG allowance price to get the heat rate. And from there, you multiply the heat rate by an emissions factor to get the marginal emissions rate. That's the gist of how that approach works. And for long-run decision-making, like what the avoided cost of a demand-side resource might be, you would use the LMP price from the day-ahead wholesale market, which better kind of represents structural changes in the market. And for real-time and short-term decision-making, like when to charge your battery in the SGIP program, for example, you use the LMP price from the real-time market, which represents better which plant would be responding in real time. And this method is I think, popular because there's a lot of price data available. It's easy to forecast and provides a good way to estimate this. But the central assumption of this estimate that natural gas is the single marginal fuel in all hours has remained unchanged for years, and it's this specific assumption that my research focuses on. And I decided to focus on this because about 8 months ago, CAISO, which operates the market on which these estimates are based, published a price performance report, which buried back on page 139, included data about what types of generating units are setting the price and thus on the margin in both the day ahead and real-time markets in CAISO. And looking at these data, we can immediately see that there's a significant issue with the underlying assumption of California's marginal emission signal. And in particular, we see that contrary to being the marginal fuel in all hours, natural gas is only the marginal fuel about 22% of the time in the real-time market, 16% of the time in the day-ahead market. And in addition, rather than there being a single predominant marginal fuel in California, there's half a dozen predominant marginal resources serving load in California. So we know that there's a potentially large flaw with the assumption of this model then, but what effect would this assumption actually have on the accuracy of the signal? Well, that's the question I sought out to answer with my research. So since we know what fuel types are marginal according to CAISO during each period, and we have a database from the US EPA telling us when each plant was generating and how much CO2 it was emitting, I wanted to identify the emissions profile of the marginal unit serving California based on the CAISO data, and also the range of possible values within which this emission rate could fall based on which units were actually generating and emitting CO2 during that period. So generally what I did is for each hour of the year, I searched for all plants in CAISO or in the regions exporting to CAISO that matched the fuel type of the marginal unit and got the descriptive statistics about these emission rates, and then multiplied those statistics by the marginal unit frequency data that was in the CAISO report to get a kind of what I'm calling a unit weighted marginal emissions factor. I also calculated a secondary estimate by multiplying the marginal unit frequency by the non-baseload emissions factor for plants of that type that came from the EPA's eGrid database. So what are the results? First looking at the real-time marginal emission signal such as that used by the SCHIP program, these two charts just show two different time periods of the marginal emission signals averaged on a quarterly basis, since the CAISO data was provided aggregated at the quarterly level. On the x-axis, we have the hour of the day. On the y-axis, we have kilograms of carbon dioxide per kilowatt hour, which is the marginal emissions rate. And the black line represents the SCHIP signal values for the three major IOU territories, which differ slightly based on the different wholesale prices in each region, but generally track together. And so this is the signal that batteries are currently responding to. And the solid red line represents the median unit weighted marginal emissions value calculated from the CAISO data, and surrounded by a light red band, which represents the interquartile range of emissions values. And the dotted red line represents the minimum possible unit weighted marginal emissions value based on that data. And then finally, the blue line there shows the unit weighted value based on that secondary method calculated from the non-baseload emissions factor. And here there's a few things that stand out that I want you to notice. First is that there's a magnitude of difference between the SCHIP signal and the data provided or estimated from CAISO, and that the CAISO data suggests that the marginal emissions rate is maybe somewhere around twice as high as what they're currently predicting. The second thing is that based on the minimum from the CAISO data is that the SCHIP signal actually falls outside the range of possible values a lot of the time. And finally, that we can see in some places where the SCHIP signal kind of spikes up and the CAISO data is suggesting actually that the emissions are going down during that period, and we can kind of see that during different periods here, not all the time, but there's definitely some negative correlations here. So looking then at the next set of data, which is the long run marginal emissions signal, such as that found in the CPUC's avoided cost calculator. We see that the magnitude of the signal here aligns much better, again, where this black line is the data from the avoided cost calculator, and then the red and blue lines are the same as described before. But there's some pretty significant negative correlations in the two signals, as we can see here, where one is suggesting that emissions are going up during these kind of morning and evening peak periods, whereas CAISO is suggesting actually that the marginal emissions rate dips down during those periods. So this is the raw results in the data, but what implications does this actually have for policy? So one of the ways I wanted to illustrate this was looking at, for example, in the SGIP program, how would these differences in the signal actually translate to real world consequences for policymaking and decarbonization of our electric grid? So what I did is I took an open source energy storage optimization model that was actually developed as part of the SGIP working group that was looking at this issue originally. And what I did is I simulated a battery to optimize based on the existing SGIP signal, basically to minimize emissions based on the patterns of when it charges and discharges. And when you plug in that same SGIP signal as the evaluation signal, what we can see is that, as expected, that energy storage that's optimizing off of the SGIP signal would be decreasing carbon emissions by about 180 metric tons per year. However, I also wanted to see, okay, so for the same battery, if it's following the SGIP signal, but in reality, the marginal emissions are closer to what the CAISO data suggests, would that still increase or decrease emissions? And when you plug in the CAISO data as the evaluation signal, we see a pretty significant increase in all months, suggesting that perhaps the energy storage resources that are following this GHG signal are in fact increasing marginal carbon emissions on the electric grid, which is the opposite of what we want to happen. So we can see that there's some real world consequences of getting these metrics correct, and making sure that we're actually seeing real world decreases in emissions rather than just modeled decreases in emissions. And so finally, what are the recommendations for kind of how we should move forward in light of these findings? Well, one option would be to simply keep using the LMP-based method, but revise some of the assumptions, such as we can no longer assume that there's a single marginal fuel, which introduces some additional complexities with the modeling, but there has been existing research such as that done by Rogers et al. In 2013 that presents a method for classifying based on the LMP price, what the likely generator fuel technology is at each price point, kind of based on a probability density. So it could be possible to adapt that method to a reality where there are multiple marginal fuels available. But the second option, I think would, and maybe one that would end up better for the accuracy of these models in the long run, would be to actually work with the market operator, work with CAISO to develop some sort of a marginal unit-based method. I mean, CAISO as the market operator maintains all of the data about which units are marginal and their fuel types and their heat rates. Even though in the past there's been a lot of confidentiality concerns, I think that probably through a concerted effort and collaboration with CAISO, these could be addressed in order to develop some sort of a marginal emission signal that's based on real world market operation. And in fact, there's several ISOs across the country, including PJM, the Southwest Power Pool, ISO Northeast, and the Mid-Continent ISO that are already publishing fuel on the margin data, such as that which I used to do this analysis. And they've found some ways to get around some of those confidentiality concerns. So that was all I had for today. I thank you for listening, and I would happy to take any questions either right now or feel free to reach out to me via email. Thank you very much.
Thanks so much, Greg. Really interesting work. And we do have a question here from someone whose audio may not be working, so I'll go ahead and read it. And then as I'm reading this one, feel free to type in your name or question, and I will go ahead and let you ask that to Greg next. So this question is, why did the CPUC adopt their methodology based on LMP and not CAISO data? It seemed like the CAISO data existed at the time the CPUC adopted their methodology.
Yeah, that's a good question. So my understanding is that this methodology was developed a long time ago by a contractor to the CPUC, and it's kind of just been updated and used for a long time. I think that basically when this was developed, probably the LMP price signal was the most available data set, and they've just continued to use that. And there hasn't really been that much information to suggest that the assumptions of this model were perhaps incorrect otherwise. Like, this was, at least to my knowledge and what I was able to find, this report that CAISO published in 8 months ago was the first time where they've actually published that type of data about what units are actually marginal. So the assumption of natural gas being marginal in all hours seemed somewhat reasonable, and based on the narrative that's told a lot in California about natural gas. So yeah, I don't know exactly why. I would guess that it was because that was the available data when this was first developed, and then it's just been recycled as a method since then, because it was something that was well known.
Okay, and we have a question from your colleague Devin here. So Devin, I'm going to unmute you. If your audio works, go ahead and ask your question. Oh, there we go.
Hey Greg, great presentation as always. Do you have any sense why emissions are decreasing during peak periods?
Yeah,
or
so
marginal emissions, I guess.
Yeah, that's a good question. And I've looked a little bit at what the data is suggesting, and it basically, like, so for example, that trend was most noticeable during in the day ahead market in some of these peaks, and this is kind of small, so it's probably going to be hard to see. And actually, this is from 2017. But what I saw initially from the data is that there's actually some flexible zero carbon resources like pumped storage that are already coming on and being the marginal generator during some of those peak periods already. So basically what I was seeing from that initial data was just that there are already some zero carbon resources that are coming in to fill that role of the marginal unit at those peak times.
And you were showing Q3 and Q4? Is the trend the same in other quarters?
Yeah, this is where it was most pronounced, and in different quarters there's slightly different trends. And so when I'm hoping to publish these results soon, which will include the full data set from through 2017 through the second quarter of 2019. But yeah, there are slightly different trends in different periods based on what units were marginal. And like for the real-time data in particular, what we see after Q2 2018 is that batteries started becoming a marginal resource a lot more significantly. And I didn't include that in here because I haven't really figured out a good way to estimate what the marginal emissions rate of a battery as a generating resource is quite yet, based on when it was charging. So I kind of left out that data for now.
Great. Okay, and we have a question coming from Patrick. He's wondering any idea of the quantity of generation on the margin. And as I ask you that, I'll unmute Patrick in case he wants to follow up.
Yeah, so the quantity, so the data that was provided by CAISO in this report didn't explicitly list, it was only a frequency value. And I spoke with the person at CAISO who had originally developed that analysis for this report. And they were saying that they think that this was weighted on based on the number of units of each generating type. But that would be something that's definitely useful to see. Like some of the data sources that are published by some of the other ISOs, like I think like PJM or MISO, actually will tell you what the marginal fuel is for each time period and how many units of that fuel type were on the margin during each period. So that type of information would be definitely helpful for refining the accuracy of that type of assumption.
Thank you.
I'm Erin Musabandesu. I'm a graduate student researcher at SWE. And today I'm going to be sharing with you some of my research on energy load shifting strategies for wastewater treatment plants. So just quickly going over the agenda of what we're going to talk about. It's a short presentation, so we'll quickly go over how the energy sector has been changing, which is something you guys are all very familiar with, and then talk a bit about wastewater treatment plants and the opportunities that they have for energy load shifting. Then we'll dive into our case study, describing that, go over our research results, and then talk about the next steps in future research. So as many of you know, California and many other states and countries have tried to increase renewable integration into the grid. And this has, in California, it's primarily been solar integration. And this has led to several operational challenges. This figure here is of the duck curve, which many of you are probably familiar with. And as the belly of the duck grows, as we increase renewable integration, primarily solar, we're seeing increased issues such as this increased ramp here and potential overgeneration. So one of the ways that the energy sector is trying to mitigate this is through energy demand management. And that's incentivizing customers to move their energy use from these peak time periods into times when energy is more readily available, particularly in the middle of the day. Sorry, I'm having issues with it progressing forward. So California does this through several different energy market mechanisms. They try to incentivize customers to change their energy use through static time of use energy rate structures, dynamic energy rate markets, such as the CAISO wholesale market, and through energy demand response programs, where they are asking you to shift your energy out of a specific time period and then just use energy as you wish during other time frames. So all of these different types of market mechanisms are used to incentivize customers to move their energy in different ways based on the needs of the grid, either in a static, dynamic, or demand response way. So the core research objective for this project, for this research, was to really investigate the ability of wastewater treatment plants to take part in these type of market mechanisms by load shifting, and to analyze the impacts of this load shifting on wastewater effluent quality. So that's the quality of the final treated water. So just a little bit more about wastewater treatment plants, because I know that that's maybe not the area of expertise of this group. So wastewater treatment plants are used to treat sewage or industrial wastewater using a combination of physical, biological, and chemical treatment processes. There's normally several different stages of these treatment processes, including pre-treatment, primary treatment, secondary treatment, and then depending on the end use needs of how clean that water needs to be for its final end use, there might also be tertiary or advanced treatment, which would include disinfection or microfiltration. So all of these different treatment processes take different amounts of energy use and can sometimes be very energy intensive. So energy actually accounts for 11 to 17% of wastewater treatment operational costs based on the size and the different treatment processes that the facility contains. So it's a significant portion of the operational costs and is very important to minimize. Many processes can be shifted to some degree within the wastewater treatment process, providing energetic flexibility. However, you know, wastewater treatment is a biological process, and part of the biological treatment components, they need consistency in flow in order to work properly. So there are limitations on how much you can interrupt certain processes start them up or delay them. But there's been research in this area, and those sort of limitations are becoming more well known. Another way that wastewater treatment plants can have energetic flexibility and do load shifting is because they have some of them have the ability to co-generate energy from the biological treatment processes through biogas production. So that was the main sort of motivation behind why we wanted to start this project. So the particular research project that we did was funded by the California Energy Commission, and SWE worked together with Train and the Laguna Wastewater Treatment Plant, which is part of Santa Rosa Water, in order to perform this case study investigating how wastewater treatment plants can perform energy load shifting. What we were looking at in particular was how wastewater treatment plants could participate in the Proxy Demand Resource Program. So the Proxy Demand Resource Program is run by CAISO, and participants bid into the day-ahead and wholesale market in order to get revenue. They bid in as supply, reducing their energy use during certain times of the day. And a minimum bid is required of 0.1 megawatts. Energy reductions are measured through the PDR program by baseline calculation. So baseline is meant to be the energy user's daily sort of energy load profile. And this baseline calculation methodology that PDR uses is the 10 and 10 day methodology. And so that's a 10-day average of eligible non-participation days. And then on the day of the actual PDR event, that baseline that's calculated, the raw baseline, which is here in the dots, is adjusted up or down based on how the actual energy load, which is in red, compares to the unadjusted baseline. And so then the final point of measurement is what's being called an adjusted baseline. So this is meant to sort of average out what your typical energy would be, and you measure the energy reduction from this typical energy baseline. The case study that we performed looked at the Laguna Wastewater Treatment Plant, which is located in Santa Rosa, California. It's a fairly large facility that serves nearly 230,000 customers and treats an average daily flow of 17.5 million gallons for recycled water reuse. And the wastewater in this facility undergoes primary, secondary, and tertiary treatment. So it has a larger energy use as well. This is a system diagram of all of the different processes for the Laguna Wastewater Treatment Plant. And because we don't have much time, I won't go into super detail of how their whole system works, but I want to sort of focus in on the three areas which our research was looking at for energy load shifting potential. And we chose these areas because we wanted to reduce the impact to wastewater treatment as much as possible, and some of the other processes are a little bit more sensitive. So the first one that we looked at is the flow equalization basin. So as wastewater enters into the system and undergoes pretreatment, after that stage, operators can choose to divert flow into this flow equalization basin. And it was estimated by the operators that if you divert flow into this basin, you could reduce system-wide energy use in order to do energy load shifting. So that was one area that we looked at. The other area that we looked at was anaerobic digestion. So that produces biogas, and then there's cogeneration. So the biogas was used by combined heat and power engines in order to generate energy. So that's also an area of energetic flexibility. And the final load shifting potential that we investigated was the Laguna Wastewater Treatment Plant, as part of this project, installed an on-site battery in order to discharge energy and help shift energy load. So as a part of our project, we performed 18 different test events of these 3 different scenarios. So again, I'm just going to kind of run through the scenarios a little bit more explicitly. So scenario 1 was to run one of the combined heat and power engines to generate energy, and that would reduce energy by estimated 1 megawatt hour. Scenario 2 was to divert flow into the flow equalization basins to reduce system-wide energy by an estimated 500 kilowatt hours. And scenario 3 was to discharge a 2 megawatt battery to offset energy used by approximately 200 kilowatt hours. So these are the results of our pilot here. I'll just run through the figures so that you can understand what it's trying to say here. So this is for the scenario 1, which was the targeted CHP use. The shaded green areas is when the facility was trying to bid into the market. So that was their targeted bid time. The orange line here is the CHP energy generation. And so you can see that the combined heat and power engine was turned on and then ran for some time and then ramped off. The blue line here is the adjusted baseline, and the blue shaded box was the same day adjustment window. And so depending on how the actual energy use and the baseline compared, the baseline was adjusted up or down as part of the calculation process. The green line here is the targeted energy load. So that's what the wastewater treatment facility was trying to hit in order to receive the promised incentive and meet the bid that they had projected. And then the red line is the actual energy use right here. So as you can see, the CHPs were generally able to target that bid window, but there was some difficulty in getting it exactly accurate because of ramping periods particularly. And so the sustained sort of meeting of the bid wasn't always possible. And you can see that there's sort of a delay here and that the target was not always met. You can also see that the baseline energy, this is meant to sort of be the projected energy use. And there can actually be a pretty large difference between, what is sort of typical use and what is actually happening on the day. And so this can kind of affect the ability for the wastewater treatment system to meet the bid as well. And particularly you can see that here, where even though there is an obviously 1 megawatt energy generation, you're not seeing any reduction from the baseline energy. These are the results for the flow diversion test events. So you can see here, this is flow into the pond, into the basin. So they were able to, target that time frame fairly well. But again, there's ramping issues. And the energy reduction is not as high as the energy reduction for the CHP. So it's more difficult to see its impacts on the energy load based on the natural oscillations of energy throughout the day for the wastewater treatment facility. And for these test events, a couple of the test events also included discharging the battery. In these final 2 test events here, you can see that the operators, I think, were trying to, help with some of the delays in energy, and the timing just was completely off. So there obviously are some issues between trying to get the timing to work, also some issues in properly measuring the energy reduction. And finally, here are the results of the targeted battery use. So here again, you can see some issues with ramping, but generally within the targeted bid area. However, the energy discharged by the battery is so minimal that it really just gets lost in the oscillations of energy use. And so this really did not seem a good way to perform energy load shifting that could be measured by CAISO's current baseline methodology. This figure here is just sort of more explicitly showing what I've already sort of talked through. So the first row here is the CHP test events. The second is the FEB test events, and the third is the battery test events. And this is showing the energy error between the actual energy load and the targeted energy load. And so you can see very few time intervals actually met or exceeded what they were hoping to do in terms of energy reduction. So some main takeaways from this is that timing demand reduction is difficult, and that the baseline is not always an accurate representation of energy use, and so can sometimes misrepresent how much energy has actually been reduced. And I know we're kind of running out of time here, so I'll try and go through this part quickly. But we also did a cost-benefit analysis to see what sort of annual revenue would be from PDR participation based on just the FEB and CHP usage, because those were the only ones that could be, somewhat accurately measured through the PDR baseline methodology. We used LMP prices from a local price node, and this analysis also included the changes of energy cost based on time of use rates. We created a projected participation model based on conversations with the wastewater treatment operators. So it was projected that they could participate in the PDR market once a day from May to October, from Tuesday to Friday. And we tested different bid windows to see if, how much the length of the bid would impact the revenue. And for this analysis, we're just trying to see what the maximum revenue potential is. And so we assumed that the bid would be timed to maximize the revenue and that all bids placed would be accepted. So this is really just the maximum that they could make from this sort of PDR participation based on the participation that they expected. So from this, you can see here, we have the different event lengths and then the different operational changes. So this particular facility, based on historical energy use and projected demand reductions and participation, could make anywhere from $8,000 to $45,000 annually participating in this, with fairly significant participation. These two activities are independent of one another, so you could actually combine them for a total revenue potential of around $68,000. As part of this analysis, we also compared the baseline energy to the actual energy. And in the same way that we saw sort of issues with this in the test events, we saw this during the cost analysis, that there was, for the most part, it's a somewhat similar and accurate representation, but there are very high outliers, which can really impact the profitability of participating in this PDR program. And as part of this pilot, the operators mentioned this, their sort of hesitancy to want to participate because of this uncertainty. So I think that that's an area that could really benefit from increased research, and so that sort of leads into our next steps. So part of what we feel like would really help wastewater treatment plants be able to participate in these type of load shifting events, besides just, practicing with the timing and trying to get those issues sort of worked out, was to increase the accuracy of the baseline calculation method so that it would be more reliable for different wastewater treatment situations. And so as part of our future research, we want to test different baseline calculation methods that would include wastewater specific data in order to increase the baseline accuracy. For this research, we're hoping to not just work with Laguna, but with other wastewater treatment facilities to test how these baseline methods would work for different treatment systems. So these are the references, and that's all I have for today. So thank you so much for continuing on with me. I know it's an extra bit of time that you stayed on to listen to this presentation. I really appreciate it. And let me know if you have any questions.
Great, thanks so much, Erin. And yeah, if you have any questions, we have some time for that. So please feel free to enter your question in the chat. I'm going to put Erin's emails up there, but I'll put it in the chat as well if you just want to email her separately as well. And then if you have any other questions for other presenters, you're welcome to ask those at this time as well.
Ali, may I ask a question?
Of course.
Erin, very nice presentation. And I was curious whether, from what you saw of this facility, could it be modified in some way so that it would be both easier for the operators to achieve demand reductions and maybe to achieve greater demand reductions? For example, have a larger, what you had a containment facility or a holding facility that could be larger, or maybe pipes just need to be wider or something so you can be more responsive. Did you get any sense of these potentials?
Yeah, so I think that there's a lot of different potentials that are open. So actually, I didn't have a lot of time to discuss this because it was such an energy bite. But part of what they did as part of this project was to add more potential. So I sort of in passing mentioned that they added a battery to the site in order to increase their load shifting potential, which it didn't work so well for large energy shifting, but it will help with sort of stabilizing and maybe smoothing out some of those ramps on the flow equalization basin or the CHP. The other thing that they did was they actually added, so the combined heat and power mixes natural gas and biogas, and so they added selective catalytic emission reduction units onto the CHPs in order so that they could run more of these power units at a time without increasing their emissions according to the air regulations. So I think that those were things that they already did. In terms of increasing the flow equalization basin, they might be hesitant because of just land use. It is a fairly large facility, so they might be able to, but also really large swings in flow can affect this treatment processes. So I think there's potential, but also some hesitancy. So I think there is still additional research that needs to be done on those kind of intermittent operations. There's a lot of other sort of processes within the system that could potentially be run intermittently as well for larger energy reductions at certain times, but the research on that is still fairly preliminary, so I think continued research in that area could really help with larger energy reductions in the future.